interrupt me through voice chat.
Absolutely.
Let me share my screen. Can you see my screen?
Yes.
Great. So perhaps the first step is installing the software, right? So I think Sylvain already sort of covered our website. So whenever you want to find us, be sure to just Google, for example, Brainstorm EEG, and we should be the very first link that comes up, right? And so to install the software, you can just go ahead and go to the download section of our website. You do need to create an account, but it's all for free. It's just for our own statistics. So if you do not have an account yet, you can create one very quickly from this link here. I already have one, so I'll just log in here. And then you have specific instructions. So there's an actual installation instruction page available. So you don't need to, take notes right now to remember how to install it. But straight from here, you can download the software and you can realize that it's actually a very small software, all things considered. Obviously, you do need to install MATLAB, which is a bigger installation, of course. But see that, for example, this source only, which is all you need if you have a licensed MATLAB installed, is only 30 megabytes. So it's a very short installation. And so for those of you, like I just said, that do have either through your university or institution, a licensed version of MATLAB, that's great. So that's sort of the best way to take advantage of the software, because you can take advantage of scripting abilities as well as exporting your brainstorm objects to MATLAB variables to work with them. So and more on this later, obviously with the demo. So for those of you that are in this situation, you can just download this zip file here. And if you do not have, a licensed MATLAB, you do need to install what we call the MATLAB MCR, or MATLAB Runtime Compiler. And it's because we also share a compiled version of the software that you can run for free using this compiler runtime. So for today, since I can demo more things using the licensed MATLAB, I'm gonna go ahead and show you how Brainstorm works in that way. So in that case, you would just need to download this 30 megabyte zip file, just extract it, and it would have a single zip file, or sorry, it would have a single folder inside the zip file called the Brainstorm 3 folder. So just open MATLAB. So I have MATLAB already started here. Navigate to this Brainstorm 3 folder and just run the Brainstorm file here, or just type Brainstorm and it will run this file. So I'll just press enter and it will start Brainstorm. As easy as that if you have MATLAB installed. So now for the purpose of the demo, I obviously already computed and populated and imported data into this protocol here. This is just to save time, so we don't, there's no downtime where we're waiting for a process to finish. But note that when you first start the software, so let me just go here to File, Load Protocol, and then Change Database Folder. So when you first start the software will ask you where you want to save your data, essentially where you want to save your database folder. This is very important because all the data that you will both import and create using the software will be saved there. So please, take good care into choosing this location. Make sure that it's not, a folder that could be potentially deleted by mistake. And also, we do strongly recommend our users to set up automatic backups. So depending on your usage, maybe daily, weekly, monthly backups, just in case something happens to your folder, either corruption or you do an operation by mistake that cannot be undone using the software, so that you can always go back and have, all of your files there, because we know that you take great care and great time into reviewing the data, doing quality control and so on. So we wouldn't want you to waste all that time. So we do recommend you to do that. Right, so this is the main Brainstorm window. So we know it's a bit gray, a bit grim, but don't worry. As we start opening figures, and I think Sylvain had great videos demonstrating that in his presentation, you'll see that, things can get very colorful and very interactive. So the first thing you'll want to do is create what we call a protocol. So you would go to File, New Protocol, and you can think of protocols as sort of your current experiment, right? Or your current research question, your current paper that you're writing. So this is, since you can only select a single protocol at a time in Brainstorm, this is sort of the highest organizational folder or level, where once you have added a file into a protocol, another protocol cannot access it. So once you have created a protocol, and I have created one right here already, which is called Workshop 01, well, you can start populating this protocol with different files, right? So over here on the left, this is what we call the Brainstorm data tree or database. And as you can imagine, this is essentially kind of like a file explorer where all of your files that you import and produce using the software will be populated and organized in a very simple fashion. So first through different subjects, then through different folders, and finally, you know, different group of files. Okay, so let's say that I just created a new protocol. The first thing I would want to do is switch to what we call the anatomy view. So this Brainstorm data tree is split into two main sort of views. The first one is the anatomy, where you would see your MRI, your surfaces, so on and so forth. And the other one, the functional view, essentially will be all of your, you know, your recording data and most of the files that you would produce during your analysis. The reason why they're split into two separate views is just because typically you'll first import your anatomy at the beginning of or when creating your protocol, and then not really touch it anymore. And so just to avoid cluttering the functional data or the data tree with too many files, we just separate them such that once your anatomy is imported and properly set up, you can sort of not worry about it and hide it from view. So once you start a protocol, like I said, you would go to the anatomy view, and the first thing you'll do is probably create a subject, right? So all of the different objects here that populate the data tree can be interacted with your mouse. And so this is a great feature of Brainstorm, where you can do most operations by avoiding any scripting. And so whenever you right click on an object here, you can see all the different operations that are available to you. So either to display or to compute from this object. So let me go at the highest organizational level, like I said, which is the protocol level, and right click. And we see that we have some basic and basic options available here. So we can edit the protocol if you want to rename it or change some general setting. We can reload it. So let's say that there was a modification on the file explorer, but it hasn't been yet updated in the Brainstorm visualization. You can just reload it from here. And finally, well, what I was going to show you today is just to create subjects. So if I click new subject here, now I can start creating or adding new subjects for my study. So you can call your subject however you think fit. And you can add some specific comments that would be sort of hidden from view at first glance, just in case you want to remember something or note something related to this subject. I don't know, maybe the participant moved, maybe you want to remember their specific age, and you don't really want to write this in the subject name directly. So that's one field or metadata field that you could add this. And finally, well, you choose two sort of settings, and the first one, or the one that I want to focus about today, is the individual or default anatomy setting. So like Sylvain mentioned, in Brainstorm, well, you can imagine that you can either import an individual subject anatomy. So let's say that this participant, you actually acquired MRI data for this participant, so you would like to use it with Brainstorm. In that case, you would select, obviously, use individual anatomy, and then go ahead and import it. But if you don't, which we know is common in EEG studies, that's okay. You can also select this option, use the protocol default anatomy, which I will select right now. Click Save. And you see that already Brainstorm sort of opened up this special subject here called default anatomy. And it's telling me, okay, so since you selected to use the default anatomy, here's the default anatomy that we've selected for you. And if you want to change it, please go ahead and do that. So right now it shows the ICBM 152 template, which I believe is sort of our by default template for healthy subjects. But if you right click here, and go to use template, you'll see that we have many other templates available. And I think Sylvain was just talking about this new contribution by our O'Reilly collaborator that added infant templates. So note that we do have that available. Just to make the installation smaller in size, it doesn't come shipped with the software, but just by selecting it right here, it would automatically download it for you and apply it to the default subject. And as you can see, we have different templates available. So here, if I open up my subject 3 that I just created, it just reminds me that the anatomy for it is the default anatomy. So that's for when you're using, a default anatomy. But if you do have an individual anatomy that was acquired for your subject, which I have for this subject 01 here, then you can also import this from the software. So if I right-click on the subject, like I mentioned, whenever you right-click on brainstorm objects, you'll see all the different operations that you can do on this particular object. So if you have computed, for example, using FreeSurfer, a surface segmentation of your subject MRI, well, you could import it in one click right here. So just go to Import Anatomy folder. Make sure that you select from the drop-down a FreeSurfer folder or whichever software you use. So notice that we have other software supported as well, BrainSuite, BrainVisa, and so on. And then double-click on whichever folder that contains the output from, for example, FreeSurfer in this example. And what Brainstorm would do is it would import first the MRI. It would ask you to set some specific fiducial points to ensure that the registration with the sensor space will be correct, and then it will import all the different surfaces as well. Notice that we have a direct import MRI option here, which in that case you don't need to actually use FreeSurfer or an external software to compute your segmentation. You can import straight the MRI, so as a Nifty, for example, file in the software, and then use, for example, I believe Sylvain mentioned this in his talk, the Cat12 MRI segmentation, which is an external software that can be accessed through MATLAB. And in that case, you can actually do your MRI segmentation in a pretty reasonable amount of time, straight from Brainstorm, essentially. So you don't need to run FreeSurfer overnight, install all the dependencies for an external software just to do this. For information, that's something that's available. I believe there was a question about DTI. So notice that we also have, for example, an import fibers option here. So if you do have DTI fibers as TrackVis file that were already computed using another software, you can also import that here. And what this will allow you to do, and I will do a demo later once we reach, a connectivity, our connectivity features, is let you display your different connectivity measures, not only using, a very crude matrix or connectivity matrix or graph, but also using the actual fibers file that you have available. And note that we do share on our website a template file that was aligned with the ICBM template, such that you can try this on any subject and see how it works. Okay, so now we have our anatomy imported. So what you'll like to do is start creating figures with the software, because this is really like Sylvain said, the strength of software is its visualization tools. So for example, for the MRI, as always, you can right-click and see what's available to you. You see that we have different display options, and the most basic one would be the MRI viewer. So let me just visualize or show you that right away. So what we're seeing here are 3 different slices for this subject. So this is, like I mentioned, a subject's individual anatomy, not a template anatomy in this case. And as you would expect, whenever you move the crosshair here, and this is pretty smooth on my end, I don't know, through the streaming, maybe there's a bit of a delay, so it looks a bit less smooth, but please believe me. You can select specific voxels here, and it will automatically update the other 2 slices. You can obviously use the slider here to go through your slices with the mouse. It shows the different coordinates, or it shows the selected coordinates, sorry, in different coordinate system over here, and you can actually choose the specific coordinate that you have selected by using this little button here, set the current coordinate, where you can type in any coordinate system that you prefer, the coordinate that you would like to access. What else can I say about this? Note that right now we're in what we call neurological view or display, where the left side of the patient is actually on the left of the screen and vice versa. If you're used to the opposite, you can toggle to radiological view here, where everything will be flipped now. So on the right or on the left side of your screen, the right side of the patient will be presented. So that's the MRI viewer. Oh, right. So whenever we open figures with color bars, this is very important in Brainstorm. So it will, first of all, show the color bar on the left or on the right side of the figure. And you can always, with your mouse, change or play with the threshold of the color bar. So here, if I click and drag and drop, for example, to the bottom here, I've just moved the threshold for the white color higher, such that everything is now darker, as you'll easily notice. And I can do so with the other way around. So you can play with contrast and brightness this way. You can also play with it manually. So if I right click anywhere on the figure and go to color map, you see that we have a contrast and brightness drop down here that you can change manually. And you can also always change the color map to a specific color map that you want. In this case, since this is an MRI, other than black and white, there's not much, I don't know, it's up to you, but I think it's very common to only stick to either bone or gray, color bar. But just for information, since this works in the same way for every color bar in the software, you can choose another color bar that you want. For example, red, white, and blue, and it will automatically update it. And you can, once again, with your mouse, play with the threshold. And whenever you've done something crazy like I just did now and want to just go back to the default color bar settings, you can always just double click on the color bar to reset it. So not so useful for the MRI viewer per se, but as we start projecting data on the MRI viewer, for example, it will probably be more interesting to play with color bars. So that's the MRI viewer. Let me close this. Another way to display the MRI is through 3D orthogonal slices. So this is now a 3D figure, and I think Sylvain had an example as well in his slides, where now the three different slices are projected on top of each other on a 3D figure. And if I right click on one, I can drag and drop and move the slice this way. And because this is now a 3D figure, it activates this surface tab. So as we get familiar with this main Brainstorm figure here, you'll notice that on the right side here, we have different tabs that actually let you interact with the current active figure or figures. And so in this case, since this is a 3D figure, it activates the surface tab, and we can actually play with these toggles here to modify on the fly what we're showing here. So obviously, if we play with transparency here, the transparency of the MRI slices will be updated. But note that we also have this plus or minus buttons here where we can add or remove other surfaces. So since all of these are aligned together, since we're all working on the same subject here, I can ask a Brainstorm to, for example, add the cortex surface on top of this MRI viewer. Now it has a lot of transparency. Let me remove it. And you can see that we now have the cortex file superimposed on top of the MRI viewer. I can smooth it out. So whenever we have cortex files, cortex surfaces, we can smooth them in order to see, below the surface what would be hidden if it wasn't smooth. And so you can activate or show or hide the sulci map in order to see whether what you're showing right now is a deep structure, so under a sulci or not. And one thing I want to mention when we're talking about cortex surfaces is this notion of edges. So let me just click to show edges here. So this is more of a computer science thing, but it's actually important to mention. So when you're representing a surface on a computer, they're actually made of thousands of different triangles, and hopefully you can see them clearly on your screen right now, Whereas the more triangles you have, the higher resolution this 3D surface that you're displaying has. And so when you're, for example, segmenting an MRI file using, for example, FreeSurfer, it will give you a Cortex file that has, you know, hundreds of thousands of vertices. So this has a super high resolution, so that's great. It will look great, but the downside is that your computer will struggle for first of all to just render it in record time, and if you want to start interacting, you know, with your surface, moving around, zooming, and so on and so forth, obviously the higher the resolution, the slower the computation will be. And also when we will project our data from the sensor space to the source space, and hopefully we will make that clearer later in the demo. But just note that all of the different edges that we're showing here, and by edges I mean all the points that intersect different triangles here, this is actually what we will use to fit, or where to fit dipoles for when we want to do source reconstruction. And so the number of vertices is actually very important here, because the more vertices that you will have, so the higher resolution the surface is, and the more dipoles you will fit. And so when you compute different measures around a source file that has many vertices, obviously this will be very computationally expensive if you have hundreds of thousands of them. This is why in Brainstorm, and whenever you're importing, you know, surfaces, we actually have a dialog prompt that will ask you how many vertices you would like to downsample the Cortex file to. And that's because, you know, if you do not downsample it, it will be very computationally expensive to do so. And so the number of vertices that we like to use typically in the Brainstorm, and this is what we suggest in our tutorial pages, is around 15,000. And that's because we believe that it's sort of a good middle ground between very high resolution surface that has tons of vertices and you know, something that is also computationally tractable, so that doesn't take forever to handle this file. And also, you know, it needs to fit in your computer's memory, which is important. So I just wanted to mention that about Cortex files. I think this is a good overview of you know, our different anatomy viewers as well as objects. So yeah, I've mentioned fibers already. Maybe I can move on to functional data if there aren't any burning questions. I'm sorry, I can't see the chat.
It's all good, Martin.
Okay.
Yeah.
Thank you.
Yes, please go ahead.
Sure. So maybe one thing I can mention right away is that notice this little crosshair button on the top right, and please don't mistake it for the actual, you know, close button of Windows. But right below, there's this crosshair button that, well, like its name suggests, it first of all closes all the open figures that Brainstorm has currently open. So right now we only have one, but we can think of situations where we'll have many figures. So it will take a long time to close them manually. But the great thing that it also does is it clears the memory. So since all figures in Brainstorm are linked, like Sylvain mentioned, together, this means that the whole data set is often in memory while you have figures open. And so it's a very good practice to use this button, you know, as frequently as possible whenever you're finished with your current visualization, because it allows, well, it allows Brainstorm to clear your memory space so that you don't, you know, run out of memory if you open too many things at once. So just for your information, whenever I close figures, I have the habit of using this button instead. So I think this is a good habit to have if you're going to use the software. So let me just close this to close the figure, and then switch now to functional data view. So now we've considered that you know, our anatomy has been properly imported and set up for this our protocol here. So what we'll do is now start populating our functional or actual recording data. So obviously the first step that we would take would be to import your, you know, original raw recordings. And so what you will do in this case, so I just press the functional data view here. Let me first work on this new subject that I created, and afterwards we can have a look at the subject that I created previously, just to save time and not actually, you know, do any computation today. So in order to import the data, so that you can start using the software, you would just right click on the subject. As usual, you'll see all the different options available to you. And what we'll want to do is import the data, but notice that we actually have two different options here. And I think the distinction is very important. So let me take a minute here to explain. So whenever you're working with raw files in electrophysiology, I'm sure, as you'll know if you've worked with it in the past, these files can get very long very rapidly, right? Whenever you have somewhat of a long recording, the size of the file will get very huge. And so in that case, in the optic of trying to save as much hard disk space as possible, what we'll do is, instead of copying the whole raw file into this Brainstorm database folder that we originally set up when we first installed the software, what you'll want to do initially, in most cases, is review the raw file here. So choose this option, review raw file, which will actually just create a link to this raw file on your computer. And so instead of making a copy, so duplicating this huge file, it will just point to it initially. And as you pre-process your data, it will not apply the pre-processing to the file itself, but rather just save it as a subroutine in the metadata of the file. So essentially, just it will remember all the different pre-processing steps that you have decided to apply to this file. And whenever you feel that you're okay, I've finished my pre-processing, this file will now be considered clean, then you can import this file. And so what you'll be actually copying in the Brainstorm database folder won't be the raw data anymore, but actually the clean data. So just in the optic that you don't want to have both the raw file or the raw data and the clean data, which once you have cleaned your data, you don't really touch the raw data anymore. You will want to create a link to this raw file instead, which is what I'll do right now. And then once the data is clean, you can import it into the software. Hopefully this was sort of clear. So what you would do is click Review Raw File here. And so whenever you're importing or creating a link to data in Brainstorm, you have to, and it's very important to remember that you need to change this drop-down here for the file type, so the type of the file that you're going to import. That's because, a bit annoyingly, in the community, a lot of different file formats share the same file extension. So we can't always just trust the file extension to know what type of file a file would be. So you sort of need to manually choose the right file type before you open your file. So in our case, this is EDF, so I've selected the EDF here. But just for your information, we have a huge amount of existing file formats already supported, so that you can import your raw file into the software, such that we're pretty confident that for most of you, right away you'll be able to import your data into the software, because most commonly used formats are already supported. And if you find that, sadly, your specific format is not supported yet, just please write to us on the forum, and we'll be happy to work with you or work with the vendor in order to add support to it, because we know this is how we can spread the tool and make it as popular as possible if it supports every possible format. So so always take care into choosing the right file type here in this dropdown. So in our case, it's EDF. And then you would just need to double click on the file and create a link to this file. So I just won't do it right now because I've done it on this other subject here. So let me close this, open the subject 1 here. And so let's ignore these 2 other folders for now. Let's assume they haven't been created yet. But my review as raw file operation would now create a folder, a raw folder actually. So we see there's little raw written on it with the name of the file that I just imported. So it was called tutorial EEG. And it will then, inside this folder, create 2 different objects. The first one, as you would expect, is a data file or raw file that links to the original raw file. And the other one would be your list of, or your channel files, so your list of different electrodes or sensors that were used during the acquisition. So for your information, in many file formats, we sort of only get the list of different names of the channels, but not much more information about them. So it's very important that you add, for example, if you have your own custom individual anatomy for this subject, which we do in this case, it's important that you add also your own EEG position points. So for example, most people, or a lot of people, I think, use Polymus in order to acquire different locations of each sensors. And so in this case, if you right click on the channel file, go to add EEG position, you can import it from a file, the points that you will have saved during your acquisition, such that all the different sensor names will be properly aligned on the cortex. When you want to, this is crucial when you will want to project this to source space. So yeah, this is very important. If you have a template anatomy, you don't necessarily need to import this from a file if you're using very typical sensor cap very typical sensors or caps, such as, for example, the 1010 or the 1020, very typical EEG caps. Well, in this case, let's say that you're using the ICBM 152 template in the anatomy. You can simply click, for example, the 1020, if that's what you use in your study, in order to get the very commonly used locations into the study. So all I meant is that for people that don't have their own anatomy and are using generic caps, or one of these caps that are already supported, and we're always looking to add support. If you believe that your cap is pretty well known in the or well used but not supported yet, we'll be happy to add the location in here. And so you don't necessarily need to import this from file if you don't have it, don't worry. So once that's properly done, you can actually double click on this and visualize your channels on top of your subject here. So here, this was 260 different channels, and notice that it was not only a cap on the head, but also on the cheeks and maybe the very beginning of the neck. And so here you can visualize if you have added all your different locations to each electrode, you can realize that they're properly projected on top of the head, such that when you will do your search space, things will be properly aligned. What you can do if you have some issues here, let me just close this. You can right click on the channel file and go to MRI registration and then edit. So if you had additional head points, for example, when you use Polymus, this is very common, I think, you can refine your registration using your additional head points. And this is actually what I did here, and it worked perfectly. But if you don't, and you need to manually fix something, either a specific electrode or the whole cap, the rotation is improper, or whatever problem there is with the registration, know that we have a manual tool here where you can do different translations, rotations, and resizing of the cap in order to make sure that you have a good manual fit of your cap on top of your head. I think that covers it for the channel file. So I think what's much more interesting is working on the raw file here. So let me double click on this. Okay, so the raw file. This is our first time we're opening a recording. So this is our time series figure here, viewer. And let's see. So now it has activated the record tab here. So this gives us all the different operations or options that we can work with using this figure here. So many things to say. Maybe the first thing would be that right now all of the signals, all of your different channels are superposed on top of each other in what we call a butterfly view. But typically, when we're reviewing through raw data, well, it's up to you, but a lot of people like to switch to column view. So this is what I'll do now. And now we'll see all of our 260 signals on top of each other inside this viewer. And so we treat this sort of raw file viewer or reviewer as sort of a book where you want to, in an ideal scenario, you want to do quality control on the whole recording yourself. And so in order to do that, well, you can use this viewer and scroll through your recording as if it was a book. And this is why we call here this a page. So what we're currently showing here, and it's actually this little red section of the whole recording. If you look at the timeline at the bottom of the figure, This is a specific page of this whole recording, and you can scroll through this recording as if it was a book by using, for example, this button here, which goes to the next page. Or I think what you'll like to use once you get familiar with the software are keyboard shortcuts. For example, F3 lets you scroll through the next recording, or the next page, sorry. And so as I press F3 here, you notice that the little red cursor at the bottom is moving forward. This little portion of the whole recording is moving forward. And you see that we're actually scrolling through the data ourselves. And maybe, you know, we can flag very easily. For example, this section looks kind of wrong. So you can easily do your data recording through this, using this, such that right, you can mark bad segments. So let's say that I find this section, you know, potentially problematic. Let me select the bigger section. Okay, let's assume this is a good selection. You can right click on the selection. Right now, I believe I have a channel selected, so let me cancel that. My mouse is, all right. Let's click here. And you can reject this time segment, for example, and notice that now there's a bad event that was created, and it's telling Brainstorm, okay, this specific time segment, there was some sort of artifact, there was a problem with the recording here, so we want to skip this from our analysis. So what Brainstorm will do is whenever you use this file or any sub file that uses part of this data, whenever there's a time sample that was inside this bad section, it will ignore it from the analysis. This can be a tool, or a very simple tool in which you can do your data reviewing, and you don't have to manually cut the data. You can always go back and edit your selection of bad segments such that you can easily do data reviewing. So let me just delete this. Go back and tell you or show you some of the things that I could show you that you can do using this rich raw file viewer. So right now we're showing 260 electrodes. This is a lot, and it's a bit hard to appreciate. So what a lot of people like to do is maybe only display a subset of electrodes at once, in order to make this more readable, especially on my small laptop screen here. So what you can do is go to this little drop down here. So right now I have all channels selected, obviously. What you can do is go to edit montages, and you can create your own selection of channels. Now I've actually made one just before this presentation where I very randomly selected about every five channels here, just to have a nice subset that correctly fits in my screen. But you're free to do whichever selection that you think would be useful for you. And what is nice is you can add a custom keyboard shortcut. So for example, here I added the Shift B shortcut, such that if I go back to the figure, let me just click to make it active. And if I press Shift B now, it will automatically only show the this montage that I've created. I just called it my montage here, so no nothing too crazy as a name. And I can always go back and go use Shift A to select all channels. So on the fly I can switch from one view to the next in order to to display only a specific section of the head, for example. So just a nice way to appreciate through the data without being overwhelmed by the number of signals. Obviously, this is only sort of a problem for people that are using over 100 electrodes. So if you have less than that, maybe it's not as necessary. So these are montages. I think I've already sort of introduced you to events, but let me properly introduce you to these. So with our recording here came two types of events, and these were actually stimuli that were presented to our subject. Just for your information, for this tutorial data that we're using, our subject was presented with left visual grading data. So they were shown two different patterns in the left eye, I believe. This is why when we we'll start seeing activity, it's mostly on the right side of the brain. And so they were presented with these very rapid visual gradings, alternating between one to the next. So this is why we have two different type of events here, alternating between this DIN2 and DIN4. And so when I select one, I can go through the recording and see exactly where these events occur, and I can look at the brain activity at this specific event. And you're also free to create your own custom events right away. So let me go to events, go to add group, I don't know, my event. And now you see that it will have automatically assigned a new color to this event. So it's orange here. And I can, through using this little time cursor that I can move using my own mouse, I can just right click or press the keyboard shortcut E, where I will add, my own event at this specific region that is of interest for me. So I can add one or multiple. Oops, now I had this DIN4 selected, so I just added it in the wrong section. Let me select my event and create another one. I think you get the point. But we also have another type of event, which I think you've seen when I created this bad section here, which are extended events. So if I drag and drop a cursor here, I can actually not just select a specific time sample, but also a time region. And so once I have selected, this time region, well, first of all, at the bottom here, we can see exactly, which time window we have selected. So the starting and ending time in milliseconds, its duration. Also, we have information about the data here. So we have the, minimal values and maximal values in volts. And finally, I can add this selection into this event, which will become then an extended event. So if I press E, you see that now it's not only a single time point, but rather a time window here that we have created for this event. And I can go through the recording, add different sections to this event. And let's say that later, after deliberations, I've decided that, okay, time segments inside this event are actually not good, they're bad. So I want to remove them from the recording or reject these time segments. When you can do this in a single click, you can just select your event here, go to events, then mark this group as bad. Then you see that it will now have the bad prefix. It will become a red color. And just like I showed before, when we would right click and reject a time segment manually, all of the time segments inside this event will now become bad. And therefore, whenever you use this file in further analysis, well, it will be, these time segments will be skipped from this using the software. Okay. So you can always play or change where your current page is at. So right now, this is the starting time of this current page. So I can, choose to go to exactly the second or the 20th second, sorry. And then you can also change the duration of your page. So far we've only shown pages that are 10 seconds long, but I can, make it much smaller if I want. For example, 1 second long here. And now we see, a much shorter or smaller page here. You can play with the gain of the signals. So the little plus and minus buttons here, or with the right click of your mouse, you can drag and drop. And so let's say that you want to see a bigger artifact, you might want to reduce the gain, or if you want to see more fine-grained details, you can increase the gain. Similarly, let me introduce you to this filter tab here. So, I think Sylvain also showed this in the presentation. If you want to sort of play around with these little filters without actually applying them to your data. So right now, since we're working on the raw file, we're sort of at the exploration stage of our pre-processing, right? And so what you can do is play with either this high, low pass or nudge filter, and it will actually apply them on the fly, or not really apply them actually. So it won't touch the data underneath, but only for, just like this little warning reminds us here, this is only for visualization, but it will, let you apply it on the current figure. So, if we low pass, obviously things will become much more smoother. So this is another way to, and I can play, or I can change this measure to whatever I want. So this is a way you can use to play around with your data and explore. I think this is, this covers a lot of things for the raw file. If I right click, so right now I just double clicked on the raw file, and what it did is automatically open up our EEG channels, so all the data-based channels. But if we right click on the data, we can, on the raw file, we can see other channels or other types of channels that are available to us. In this case, we see that we had the ECG, the electrocardiogram, available. So if I go to display time series, so right now I have very short pages. Let me go back to 10 seconds. And you can see here that we have, since this was available in our recording, so the participant had an electrocardiogram attached to them. And so we can see now the different heartbeats very clearly on the recording. And notice that it actually opened this as a separate figure. And so this is, as Sylvain mentioned, one of the strengths of Brainstorm, where you can, since all of the figures are linked together, whenever I'm, advancing the time cursor in one figure, it is reflected in the other figure. So if I do, a time selection on one figure, the other figure is also updated. And so this is another way to show, other modalities straight from the raw viewer. So given that we have heartbeats, we know also that we have eye blinks. Let me now introduce you to artifact cleaning using Brainstorm. So from the record tab, you see that we have, let me make sure I'm selecting my raw file here. Great. You see that we have this artifact section here. First of all, very important in EEG, you can apply an average reference to your whole recording by choosing this first option here, re-reference EEG. You can actually re-reference your EEG, all of your data, either on a specific channel. I think this is explained here, either on a specific channel, or if you want the average reference, you can just type average, and it will compute what we call a projector in Brainstorm. So let me go to artifacts and select active projectors. So now I've already computed a blink projector. So maybe let me do the average. I believe I had done it, but I guess not. Let me run here this re-reference EEG in the average, and notice now that we have a new projector that was added, and this is actually you can actually toggle this on the fly. So whenever you're exploring your data, so right now it is active, but you can unselect it, so make it non-active, and it would automatically apply it to the data. I believe it's a bit too subtle here, so we can't see it, but with the blink, you'll see the difference right away. So if I go back to artifact cleaning, sorry for the little sidetrack. So you can, first of all, detect different specific events that might be artifacts. So heartbeats is a very clear one. If you have an ECG here, you can very easily detect events centered around this signal. So let me do this right away. If you go to artifacts and detect heartbeats, you tell Brainstorm which channel you would like to use to detect, when an actual event, so heartbeat event occurs. In our case, it's the ECG signal, obviously, and it will create an event centered around the center of each of these stimuli, right? So let's call it cardiac, which is the default. I think it makes a lot of sense. So now what Brainstorm does is goes through the whole recording. It finds the peak of this ECG signal and creates an event centered around it. So we see that we now have 700 cardiac events, which are exactly, which will exactly align with our ECG here, such that, the cardiac event here is exactly aligned here. If I right click, so let me show you another way to display events. If I right click here, go to display options, events, and then lines. Now, instead of a dot, each event would actually be displayed as a line, so you can exactly see, precisely where in the recording the peak of your heartbeat occurred. So if you're looking at investigating artifacts, this can be useful. Let me just go back because it clutters a lot the screen. Go back to dots. Okay, so this is heartbeats, but you can also do the same with eye blinks. And this is what I'll demo today just because it's so, the difference is so obvious night and day when you correct an eye blink artifact that even through, my average internet connections, I'm sure you'll be able to see the difference. So if I go to, well, first of all, in order to do that, we do need some sort of an electrode that tracks the eye movement, right? So either a electrooculogram. So if you have a vertical electrooculogram that tracks the eye, then you can easily see, detect when an eye movement occurred. But if you don't have it, that's also okay, because we have electrodes that are very close to the eyes, and you can use this in order to detect eye blinks. So let me just show you how we're going to do this here. We do not have an EOG. So let me display the data in the 3D, where you can actually see the electrodes, the electrode placement. Let me make this bigger here. So now we have all of the electrodes that I have selected for this analysis here. And if I show the label here, great. So we see that we have many candidate electrodes that are very close to the eye. That might be a good sort of replacement if we don't have an EOG to detect eye blinks. We've decided to go with 25 in this case, but just for your information, probably that 32 or even 18 and 37 would have been fine. So it's up to you, and you can play around and see. So this, just for your information, this is why I'm going to select 25 here in the artifact detection. But if you have obviously an EOG, this is even better, and this is the channel that you would select. So if I go back here to the raw file, go to artifact, and this time detect eye blinks. And like I mentioned, this time I will choose this channel number 25 for this exact reason that I just highlighted. Let's call it blink. I think it's pretty obvious, pretty straightforward. And then what it does is creates different types of events here. The main one being, very clear blink events according to Brainstorm. And if I select one here and increase, the gain here, we can see that there is a huge artifact around these two blink events that are, very most likely just an eye blink by the subject. So for this reason, this is very important to clean this. And as you'll see, it's very obvious when we apply the correction how much the artifact was attenuated. Just for your information, there are other blink events here that were created, blink number 2, 3, or 4. And these are other types of event that are a bit less, and they're a bit less, how should I say, they're a bit longer, I guess. They last a bit longer, so they're possibly, not exactly an eye blink, but they could be what we call saccades, where the participant's eyes move from one side to the other. So they might not be, pure eye blinks. But if you feel that they are eye blinks, you can always, for example, group events together. So if I select both blink event here and go to event and then merge groups, then they would be merged into a single group. But just for the case of the demonstration today, let's just focus on this first very clear blink event here. So let me go back to artifacts. And now that we have detected, our events, we can now apply a correction. So, here in in Montreal, we like to use what we call SSP, which is essentially a PCA-based approach to artifact cleaning. But we also have ICA, supported. We know that it's also very popular in the EEG community. So feel free to select that if this is what you're more comfortable with. But just because SSP is so straightforward, let me select this for the purpose of this demo. So SSP eye blinks. So we choose which event we would like to use to detect, eye blinks. We've already detected them using the blink event. So let's select that. We need to select the sensors or data sensors that we like to apply the correction on. So for us, we don't have MEG, but that's okay. It will simply return nothing in terms of MEG-based sensors, and EEG will return all of our data sensors. So that's perfect. Let's click run. So now it goes through the whole recording. It centers, a time window around each of our blink events, and it extracts, it does principal component analysis on this signal, and it extracts the different components that are most explained by the blinks. So notice that now it just applied the correction by default, and notice that now our gain has gone through the roof, and that's precisely because most of the signal was most of the difference in signal was contributed by the blink. So let me just unselect it, and you'll see the difference. Let me go to actually a real blink event, sorry. Like here, great. So let's focus, for example, on these two blinks, very clear blinks. And when I apply the correction, it's basically gone. So this is a great way to correct for this artifact. You can actually visualize the component that you're moving. So let's say I select the first 5 components and add a topography here. it will show you the contribution of each of these components here, and we see that the components very near, or the first component here, which explain 44% of the variance, which is huge. It was essentially only the electrodes very, very close to the eye, so it's pretty much expected that this is a proper blink component that we would like to remove. Maybe the second one also, although it's a bit more debatable, whereas the rest, it affects electrodes much farther from the eye, so we wouldn't want to touch it. So I think just selecting the first component in this case is a great correction. So if I click save, well, like I mentioned, you can always, with these projectors, since we're working on a raw file, none of the actual data is modified yet. This is just ad hoc or on the fly pre-processing. And when we'll be ready to import this data, we can just apply the projectors that we want, such that the clean data that we import, or the data that we actually import, is clean and has applied these different corrections. So since I have 2 blink events, let me just remove the other one. Great. And if I click save, it will remember these 2 projectors. And so you would like to continue or to go through your whole recordings manually. It's always very important. And we want the software to be as smart as possible to save you time when you're doing data or quality control. So we have these tools, these artifacts detection tools, for very common artifacts such as heartbeats and eye blinks that can automatically clean this for you, so you don't lose this data. And just for your information, we also have this detect other artifact process that sort of automatically goes through the recording and finds very low frequency and high frequency sections that are potentially noise or potentially artifacts that you would like to exclude. So this process, it's a bit slow, so I won't run it today, but just for information, this process goes through the whole recording and so finds these regions that are potentially problematic. So then you can go through these regions manually and approve essentially whether you want to mark them as bad or not, and you can play with the sensitivity here depending on your data. So these are, I think this is a good overview of the different pre-processing tools that you have available straight from the raw file. So we do have some, some measures or frequency measures that can be produced, such as, power spectrum density. And so in order to do that, let me introduce you to another section of the main brainstorm window, which is the process box at the bottom here. So you can think of this as sort of a data bucket where you drag and drop different objects here. So let me drag and drop our raw file, and let me just close it. So you can drag and drop different files and then run, like Sylvain nicely introduced, run different processing, and you can think of them as sort of building blocks of an analysis or a processing pipeline on these files. So everything that you drag and drop here will be sort of inputs of these different processes. So if I click run here, it opens up a pipeline editor that lets me add 1 or more processes that will be applied to this raw file. If I click on the wheel here, it will let me add processes, and they are grouped by different types of processes. Let me highlight some of them since we're talking about pre-processing. So under pre-process, we have very basic but very useful filters here. For example, you can bandpass filter. So notice that we had this filter tab that let us do this on the fly, but this wasn't actually applied to the data. So if you want to actually apply a filter to the data, you can choose bandpass here. Similarly, bandstop, notch filters, which are very important, when we're working with power line artifacts, and so on and so forth. So under artifacts, we'll actually see some of the processes that we just run through the GUI, but you can also run them as processes. And what I wanted to show you today is the power spectrum density, which is under frequency here, just because it's such a nice way to evaluate the quality and the signal to noise ratio of our data. So if you click power spectrum density here, we've now selected our first process into our pipeline. We can now choose different options to this process. So we will like to run it on the whole file. So let me check all file here, but if you wanted to run it on a specific time window, you could do that. This is a bit more advanced, but you can choose the window length and overlap ratio, which is how this power spectrum density is actually computed for you signal processing geeks. You can also, into more advanced options here, you could group your different frequencies into specific frequency bands, and these can either be default well-known bands, but also you can write your own specific bands. So I could choose the value of alpha. Let's say I'm working with this specific pathology group or older patients. But let me just stick to the default for today. And actually, I've already run this just to save some time, but just for information. So now that we have created a pipeline with a single process, we could either run it right now. So if I click run, it would right away produce this this child file here, which is a PSD of this raw file. But just like Sylvain nicely demoed earlier, you can also save this pipeline. Now it's only a single process, so it's not as interesting, but you can think of adding multiple processes that would run sequentially, and now it would be more meaty or more useful thing that you would want to reuse. So you could save this to reuse later, share it to a collaborator, or just like Sylvain mentioned, you can also generate the script in order to do that and to use it later or share it even. Okay, so I've already computed this PSD here. So let me just clear this list, open up the PSD. And so I'm assuming most of you are familiar with power spectrum density. So here on the x-axis, we have, different frequency. I believe this was 1000 Hertz data. So it stops at 500 here. And on the y-axis, we have the power of each frequency. And as you can imagine, the power at early frequencies is much higher than, power at lower frequencies. This is actually why right now we're showing a log of the power. So if we plotted the pure power, you would see how the early frequencies completely sort of annihilate, right, the rest of the frequencies, the lower frequencies. So if I stick to the log of the power, you can see, first of all, that there are very clear artifact peaks at around 60 Hertz, and it's harmonic. So we see a very clear one also at 300 Hertz. So this is the power line frequency that I was briefly mentioning about. So since this data was acquired in North America, our electric current runs at 60 Hertz. So this is something that creates artifacts, very clear artifacts in our equipment. And this is something that we need to, correct. So this is where a notch filter, for example, would be very useful in order to correct this. So let me maybe zoom in on, the lower part of this power spectrum here. I think it's much more interesting. And you can also, so this is, the power of Brainstorm, all of these little figures that are connected to each other. If I right click, I can also add a sensor cap visualization where, wherever we have our time cursor, which is actually now a frequency cursor selected, we can actually see where most of the contribution of each, frequency is coming from. So the very low frequency seems to be coming almost exclusively from very, close to the eye's electrodes. So as you can imagine, this is most likely, eye artifacts. So this is something that you want to correct. By the way, this PSD was computed on a non-cleaned data. So there's no artifact correction just yet. If we move forward to around 10 Hertz, we'll have our very expected alpha response, as well as, still some eye artifacts. And actually, I think they stay there, the whole frequency spectrum almost. So this is why it's very important to clean. Around 20 Hertz, we have, the beta expected response. And so from this view, you can already appreciate, the quality of your data. You could also flag some specific channels. So if I select some signals here and right click on them, these are specific channels that might be, problematic. And so you can, not only you can reject time segments in your recording, but you can also reject channels altogether. Obviously, this is because we have so many electrodes available with 260 that gives us this ability or this possibility. And so if I select some channels and right click on them and mark selected as bad, then all these channels will be ignored from further analysis. Was there a question, Sylvain?
I wanted to mention, sorry, Martin, that we have about 30 minutes left. So I think maybe you could close
Yeah,
these aspects now and wrap up these aspects quickly so that you can import a few trials and
sure,
illustrate the source mapping.
for sure. Yeah, thank
Okay,
you for
thank you.
keeping track of the time.
Problem.
Okay, so right, this is the power spectrum density. Let me close this. And what I'm going to show now is, so let's say that we now, assume that our pre-processing is sort of done. Obviously, we went very quickly today over it, but so what I did here is I high-pass filtered the data as well. So this is why there's a second sort of folder here with the high suffix here. We see that I high-pass filtered the data as 0.5 hertz. But yeah, let's say that we're happy with all of our artifact corrections that we've made, all of our filtering. Now we can actually import the data. So far it's only been links to raw file as indicated by this little icon. So to properly import the data, let me right click on the data and go to import in database. And so now we can choose, now we can choose all of our options in order to import actual data files. And since this is a stimulus-based experiment, we will actually want to center different epochs or trials around our stimulus of interest. So in our case, it was two different types of visual grading, DIN 2 and DIN 4. So highlighted as these two events, I mean. And so I will select these two events. If you wanted to do a resting state, for example, analysis, then you would not select any event. Rather, you would just select, the time window of interest. But here we'll just extract epochs around these specific events. You can choose the time of your epoch. So it's very important to choose some time before the stimulus presentation, just because you can get a nice little baseline of brain activity before the brain was subjected to your stimulus. And then also you need to choose some time after the stimulus in order to capture, obviously, the brain response. But you don't want this to be too long such that it overlaps with the next stimulus. And recall that these were actually very closely, very, very short stimulus close together. So let me write type a very short epoch time to make sure we have no overlap. And this is where, like I mentioned, we would actually apply our cleaning here. So we do want to apply our projectors that we've computed. If you want to, for example, remove the DC offset, either on the whole recording on a specific time range using the baseline, for example, we would do this now. Since we're going to use the baseline as the noise sort of estimation for our analysis, then we won't do any DC analysis in this case. You could, resample the recording if you find that the sampling rate is too high, and then just click import. So this was already done, and what it did is it created 396 trial files or data files, and for each event, and where the center, so the time number 0. Let me open one to make it very obvious to you. So it created two groups of files, right, for each event type. If I open the first one, let me this time group together and display all channels. So now at time 0 is our stimulus presentation. Before that is sort of our baseline, and after that is our brain response. So when we're looking at individual trial level, as you can imagine, it's extremely noisy, right? This is why we gather many different trials, such that we can average them together and extract in ERP, for instance. So just before we do that, one more way to sort of visualize these all of the trials together, you can right-click on the group of trial and display them as image. So let me display the EEG data. So what it will do is it will overlap all of the different trials as signals, and now we're going through the data, channel by channel. So this is just the first channel, and even though when we're looking at individual trials, it's very noisy, we can already sort of appreciate that around 100 millisecond, we have a very clear, negative peak of activity, followed by a very clear positive peak of activity. Even though it's not, perfect and even amongst all trials, we do see the trend emerging. So when we will do our average, it will be very clear that it will show up in the ERP. one more very quick detail. If I open, for example, the second trial here, notice that part of the data was part of this bad sort of section or segment that I had flagged. So because of this, there's this little exclamation red exclamation mark here telling us that this trial will be or is bad. So it will be actually disregarded for the rest of the analysis. And I can always right click and accept it again, or similarly mark a good one as bad from here. And so here we had 296 files, but if I drag and drop them into the process box, we actually only have 260 good files that will be used when we do run any processing on them. Okay, so what I did is I dragged and dropped these two groups of files together, and I just run a very simple process, averaging process. And so let me open up this DIN2 average process. And thanks to the power of having that many trials, we can very easily, the trend very easily comes out of the data. And so we see that we have a very nice, peak at around, I don't know, 100 and something millisecond, and another peak at around, 150 milliseconds. So it's very clear that the brain response of for this data. And just to show you, how all of these figures are linked together. So let me open up a topography as well. So once again, the stimulus is presented at 0 milliseconds. So before the stimulus, the data is sort of all over the place. But as we reach, the very nice peak of activity, we see our first sort of peak on the topography, and then it inverts to the next peak around 150 milliseconds. So great and easy way to explore data from averaging trials together. So maybe let me move on to now source space. So what we've been showing so far, obviously, so if I switch to column view here, we see that we're working with 260 signals at the sensor space. But what we would like to do, if we do have anatomy, is to project this into the brain of our participants, so as to figure out exactly, where this data is coming from. From the topography, it's not very clear the exact brain region where the data, where the activity is. It's a bit, crude. So if we can project it to the source space, then we can get, very precise measurement of where the activity is. So in order to do that, we need to compute three things. So I won't go into too much detail today, but the first thing we need to do, if you right click on this, the channel file, is to compute first the head model. And so you have, either Cortex or MRI based head models available in the software. We like to use for EEG boundary element model, but we also have simpler three-shell sphere model available. And we're also we have also added a very new addition, which is this finite element model from the Neuro. So I've chosen the BEM model here. In order to compute the source space, we also, or project it to the source space, we also need a measurement of the noise, since we're going to do minimum norm imaging for source model. So in order to do that, I just selected all my trials, right-click on them, went to noise covariance, and I computed from recordings. And actually, I used this 100 millisecond baseline before each stimulus presentation as sort of my measure of noise. So if you have, for example, an empty room recording, I guess in EEG it's not as used, but in MEG, this is what we do. This could also be a nice measure of the noise covariance. So this is just a channel by channel matrix measuring, the noise of the different channels. And finally, we do need a source model. So if you right click on the head model, once you do have a nice noise estimation, you can go to compute sources. So like I mentioned, what we're going to do today is the minimum norm imaging. So this uses the measure of noise in order to do a nice projection to the source space. You can also add different measures, so I won't have time to detail them today. We have a nice and thorough tutorial page specifically on source imaging on our website. And you can also choose where you want to fit the dipoles. So recall that I talked to you about these little vertices. So these intersection of different triangles on the Cortex file, Cortex surface. So this is where exactly each dipoles will be fit, and you can choose how many dipoles will be fit at each point. So either only one, which is the constraint model, which will always be, it will always fit a dipole normal to this cortex file, or you can choose either a loose or unconstrained model, which will fit 3 orthogonal dipoles at each location. If you choose loose constraint, it's just that the normal sort of dipole, so the normal direction dipole, will have a higher proportion of power than the other 2 directions. So I believe in my case, I did a DSPM and unconstrained, so 3 dipoles model. And what it created is this little inversion matrix here, an inversion kernel that actually all alone, you can't do much with it. But what is nice is that now all of our data recordings that we've already produced, they now have a new child object, which is actually a link to this projection matrix, such that whenever I open this data file in source space instead, it simply projects on the fly all of the data in the sensor space to the source space. So let me show you this in action. So let me first of all go back to our nice little ERP that we had here, maybe with the topography as well. Great. And so now that we have actually projected this to the source space, let me open up this surface, cortex surface here. And we actually see that now we have a much more precise location. And now I have some scouts selected. I could hide them so that you're not too distracted. You can see that I have a much more fine-grained location of where the activity of this stimulus is in the brain. And if once again, all of these figures are time linked together. So as I move forward in time with my time cursor from the recording figure, we see that now the data starts showing up in our source in our cortex viewer. Just for information, this is thresholded based on the maximum amplitude. So this is why at some points we don't see much activity on the cortex. I could lower this threshold, in order to show more. Just to highlight that we really want to show, regions that have a high, amplitude of activity. And so, as I move forward, we can identify specific regions that might have, that might explain this sensor space activity. And, when we go to the second lobe here, we have, smaller regions, more of it on the right side here. So I hope this gives you a good sense of, first of all, how all of the figures are linked together, and also, how much more precise of a measurement you can get when you project your data to the source space. If we want to start grouping together, these different regions, or studying regions, what you'll do is you go to the Scout tab, and if you select User Scouts, you can actually create your own regions. So if I click this little crosshair here, let's say that this region seems of interest to me. So I just clicked on a specific vertex here, so it's only a single point, but I can actually grow this region manually myself. Let me make it clear now. So I haven't named this region anything meaningful, so it's just 4 here, but I can grow this region, and I can actually summarize all of the different source time series that are inside this region into a single time series, so that if I want to start doing different analysis, it can be a good idea to summarize these into specific time series. So let me just click the display Scout time series here. And even though we have 115 vertices into this region here, so we would have 115 signals, we can summarize them into a single signal here, and we see that it also has the 2 modes that we had found in our ERP. Similarly, we could, if I close this, I could overlay multiple regions together. So let me make sure I'm overlaying our scouts here. And when I display the time series, and now the different signals selected are actually an aggregation of each of my regions here. So this this is a nice way to explore our data in the source space. Just for information, since we instructed this through FreeSurfer, we do have access to some commonly known or well-defined atlases in the literature. For example, the MindBoggle Atlas, which contains well-defined regions of the brain, so that you don't really always have to create your own custom regions depending on your analysis. It can be nice to compute analysis on very specific or well-defined regions. And actually, let me just end by giving you an example of connectivity, of a connectivity result, and then maybe we can open the floor to more specific questions. Just, I want to make sure we don't run out of time here. So let me just give you an example where we compute, a very simple correlation of all of the different regions defined by the specific atlas, which is the MindBoggle. And actually, I can also give you a demo of the fiber visualization using this. So let me close all of this. Hopefully, I didn't lose all of you guys. So I have imported, a chunk of resting state data here, about 25 seconds or 35 seconds of the raw recording. Well, it's cleaned now. And using this, this projected into the source space, I can drag and drop the source space link into my process box and go to run. And if we go under connectivity, you can see all of the different connectivity measures that we have supported in the software. Just for today, we're going to use very simple correlation. Notice that many of them have sort of two versions, so correlation 1 by n versus n by n. This is simply because either you want to compute the correlation from one region to all the others, or if you're doing more, exploratory or general analysis, you want to compute all possible pairs of correlation between all possible pairs of region. So this is actually, a huge number of comparisons. So this is why it's important to maybe apply a scout function before, such that, we don't want to run this on all of our 15,000 signals, because, all different pairs of 15,000 signals starts being, very untractable, and my poor little laptop will never finish computing and probably run out of memory. So what you can do is select, first of all, different regions in which you can summarize or aggregate your 15,000 signals. So this is why I was talking about the MindBoggle Atlas here. I can run some sort of aggregation function, so as simple as a mean, a max, or for example, a PCA if we want to extract, a signal that explains the most of our signals of each region. And I'm going to make sure to run this before, so I'm going to aggregate my signals before I do my connectivity. Otherwise, I will have 15,000 by 15,000 comparisons. And finally, save this as a connectivity result. And I have done this right here already. I've already computed it, and I've actually projected it. So if you right-click on a surface file, I can always project a source to a different anatomy. What I've done here is I've projected it onto the default, ICBM 152 anatomy template, such that now I can take advantage of my fiber tracking, or my fiber tracks that I have imported that were aligned to this template, because my subject's anatomy did not have DTI. So let me just show you the result of this connectivity result. So remember, this is a correlation using this MindBoggle Atlas. Let me first just display it as a connectivity graph. So as you would expect, well, here, if I just select a single pixel, it will show you exactly what I'm comparing here. So I'm comparing these two specific regions together, and they actually are very correlated. We see that their correlation score is close to 1, so 0.95. This is super high. And we see that, other regions are much less, correlated to one another. This is almost nothing. And so, we know that this is typically reported in papers, but it's not flashy enough for us, and it's not very nice to export data. So this is why we've added some other figures to display this connectivity matrix. If I just close this, right-click on it, we have first of all, the display as graph, and we also have display fibers. This newer feature that I have added. Since I have imported the fibers, this is also available to us. Let me just briefly introduce the graph, and then I can show you the fibers and open the floor for questions. So I selected graph here. So now what we're showing is all the regions that we've chosen, and these were from the MindBoggle Atlas, that we've used to aggregate our signals into these 60-something regions. And now they're all plotted around this circle. They're grouped together by lobe. So for example, these 3 regions together are part of the same lobe. And they're also separated by hemisphere. So all of the regions on the left obviously belong to the left hemisphere and vice versa. And what we have here, thanks to the display tab, is an intensity threshold based on our measure. So this is a correlation. So as I lower my threshold here, I'm showing more and more connections, right? So all the connections shown are connections that, for example, have at least 0.80 correlation score. So this can be a nice way to sort of go through the data and find that, for example, only these regions have very high correlation score. Maybe I only want to see, connections that are between hemispheres. So I don't really care about the connections that are between, or within lobe. So we can see here that, only these regions have this correlation score. So this is just a nicer way, perhaps up to you, to interact with this connectivity matrix. We also have a filtering based, or distance filtering based threshold. So, maybe we only want connections that are at least a certain length in millimeters. So we can play with this as well. And finally, let me end with this. You can right click and display fibers. And so we're going to have the same graph display as I had before, but we'll also plot. So this takes a little bit of time because it assigns on the fly all of our fibers, our DTI fibers that were extracted using, a tracking algorithm through another software to our atlas that we've chosen. So each different region now will have an atlas associated to them, such that we can sort of get better idea of which regions we're showing right now. For example, if we only choose, this connection, now we know exactly, okay, it's this connection in the brain, so it connects precisely these 2 regions here. And as I lower, so let me just cancel this selection here. As I lower my intensity threshold, we're going to start seeing more and more regions. And as you'd expect, we will plot more and more fibers. And here the color bar are both linked. And it's once again, the correlation score here that we're plotting. So if I modify the color bar here, it will modify, the color of the connections and the fibers. And finally, we have some, specific toggles here that we can restrict what we're plotting. For example, I can only show connections between hemisphere. So we'll expect, only fibers that go through, for example, the corpus callosum or go through both hemispheres that are now shown. And similarly, let me show you this last toggle here, which only shows connections, for example, that are, and here we need quotes, but anatomically accurate, meaning that only connections that have an associated fiber in my fiber file would be shown here. So I can, restrict this. Obviously, right now I'm showing so many connections that it's a bit hard to make any sort of meaningful conclusion here. But hopefully, with this tool, you can sort of, it can help you